So in this video, we're just going to look at some tricks in terms of reading thermodynamic tables. The tables we're going to look at are from Robie et al. 1979. So you can download this from the web if you want to follow along. So Robie et al. 1979 is a very famous compilation of thermodynamic data. And we're looking at page 15 in that document. It also, I think this is page 329, the listing for anglicite, which is lead sulfate, PbSO4. Now, these charts, these tables are giving us data for formation from the elements, the enthalpy and Gibbs free energy of formation from the elements. Now, what we want to do is just check for internal consistency. From another video, we show that delta G is equal to delta H minus T times delta S. We want to show that that's going to work for these fellows here. So we're going to look at this fellow here, anglicite, formation from the elements. What does that mean? We have PbSO4. That's what we're going to make. Those are our products. And to make it from the elements, we are going to take metallic lead and then add it to sulfur. This would be the yellow material you'd see in a mineralogy class. And then we need oxygen. We usually have oxygen listed as O2 gas. And since we have 4 oxygens there, we'll have to take 2 of those units. Notice that this is metallic lead, not ionic lead. So when we start looking at this table over here, we want to look at values for lead when it's in the neutral state, not the 2+, for example. And then the same thing for sulfur. Sulfur can be a charged atom. It can be an anion or a cation, but we want sulfur in the neutral state. Again, when it's in that yellow form that you would see in a mineralogy class. And then this would be for O2 gas, which is out of the field of view. So when they list the enthalpy here, that is the heat of formation, which we can write as this, delta H sub F, which would be the enthalpy of anglicite. Just write it like that, ANGL, minus the enthalpy of lead, minus the enthalpy of sulfur, minus 2 enthalpy units of O2 gas. Now, we don't have to do any calculations here because it's already given to us. It's right there, minus 919.94, and that's in units of kilojoules per mole. So that gives us this value here, and we know the temperature. It's listed at 298.15, so we have this. But what about delta S? Delta S, this is one of the tricky parts. The delta S for this formation is not given in this table. It is not this. This is the entropy of anglicite at 298.15, and we would have to subtract from that the entropy of lead minus the entropy of sulfur, that's an S, minus 2 entropy units of O2 gas. And we can get that from this table over here in 15. So that's kind of a trick. This is a delta H over here, and this is a delta G for the change in Gibbs free energy. We could put a subscript F for formation, but this is not. This is just the entropy of anglicite itself. So if you want this delta S value, and in this case we do, to calculate delta G, we have to take this S and then subtract it from the values here. And what we'll show here is here over in the second column is the entropy in joules per mole dot K. We want this guy here. Let's erase the chalkboard and do, we've already got this value here, delta HF, so we already know what that is. We're just going to do this calculation right there for the delta S. So if we just get rid of all this, then the delta S for the formation of anglicite would be the entropy of anglicite, which is listed as 148.57, and that's the value that we get right there, minus the entropy for lead, so that's 65.06. You can rewind the video and look at that. And then we have the minus the entropy of sulfur, which is 31.8 joules per mole dot Kelvin. And then it was out of the field of view, but if you look lower down on page 15 or 16, you'll see that we'll take 2 units of the entropy of oxygen, which are 205.15 joules per mole dot Kelvin. And if we take the sum of all those, Then we get minus 358.59 joules per mole dot K. That's an M4 mole. So that's the delta S. So for the calculation of delta G is equal to delta H minus T times delta S. This is the delta S that we're going to have to use. But there is one other minor correction. Now the delta H here is given at minus 919.94. That's in kilojoules per mole. We're going to have to convert this to kilojoules per mole as well. And so we want joules to cancel. We'll put joules up here. We want kilojoules on top. There are 1,000 joules in 1 kilojoule. So we'll take that divided by 1,000. And so delta S will be 0.359, 5859, we'll carry it out. And so that is the delta S that we will multiply by temperature. And so the temperature is 298.15. Can we squeeze it all in? It's kind of sloppily written, but hopefully you get the idea. Basically, this number here is that number divided by 1,000. And when we do that calculation, we find out that we get the number of minus 813.026 kilojoules per mole. Does that work with what is listed in the table? Yes, there it is. So this equation, delta G equals delta H minus T delta S, does give us the right value. So these things all do make sense, so long as you don't mistake this for a delta S, which it is not. And then for the final calculation, how about this log Kf? In another video, we showed that RTlnK, where we use the equilibrium constant, is equal to minus delta G naught. Well, instead of equilibrium, we can just consider this the sub F because the F is for the heat of formation. So we can make the same kind of substitution. And so we can, well, this is base 10 log. So if we solve for, let's get rid of all this mess. If we have RTlnK sub F equals minus delta G naught, that's the Gibbs free energy of the pure substances, which we just figured out here, but it's already listed. We're going to use our calculated value to see how close it comes to this value here. Well, it ends up our calculated value is identical to that one. Let's see how it works out. That means the natural log of this equilibrium constant, which is for the formation of the elements, is equal to minus delta G divided by RT. And if we want this to be a base 10 log, then we have to add one more correction. It will be minus delta G naught over RT times 2.303. That's our correction to get from a natural log to a base 10 log. Now over here, if we're going to use the gas constant R in units of joules per mole dot Kelvin, it's about 8.3144. That's in joules per mole dot Kelvin. And that means this has to be in joules also, not kilojoules. So we had minus 813 before for kilojoules. So that means that we would have minus 813,026 joules on top. And then the gas constant multiplied by 298.15. And then multiplied again, we're running out of room, 2.303. We will get, as a calculation, 142.41. That's pretty close to this value of 142.439, but not quite. I'm not sure if that's rounding error. It might be, or it could be they do a little bit of modeling to get the log KF instead of taking a calculated value from this. I'm not precisely sure. It could be that they had other decimals out here, though, that gave us that slight error. But this at least shows us that tables are internally consistent, provided that, of course, we read them correctly and not mistake things like this. And there's a big one. Don't mistake that for delta S. It is not a delta S. It is just the entropy of this stuff here at that temperature of 298.15.